What I'm going to talk today is essentially an ongoing work with three Spanish persons. Most of the work I'm presenting now is actually with Spanish people. The three ones I'm working with are Pablo Arias, Jacinto Martín from University of Extremadura, and Alfonso Suarez from Universidad de Cádiz. And my talk essentially was aimed to young audience. In general, when I come to these conferences in Latin America, there are many, many young people. Today there are less, so I made some small mistake about my prior beliefs. Okay, but so that's an issue. Choice of prior distribution is, you have to be very careful, which essentially is this take-home message which I wanted to tell to the young people. Let's go Bayesians, but be careful. Because one of the points I'm very, very interested right now, is about how we do perform Bayesian analysis. At the very beginning, you have seen a lot of sophisticated models, and CNC, and so on. If you come next week to Belo Horizonte, I will give a more sophisticated talk about stochastic partial differential equation applied to heat equation, and a lot of stuff I was mentioning before when there was a previous speaker in the previous section. So that will be something different. But something I've been very interested in is been working with people in companies, especially engineers. So the point here is to go back to what is essentially the core of the Bayesian approach. So essentially, these are the points. We have to use experts' opinion when they are available. I try to use them as much as possible, and we always forget about that. Also extract as much information as we can from them, and use all the information we get from the expert, and add nothing else. So sometimes when I see someone using, for example, a gamma 3-5 prior distribution, my question is, why gamma, why 3, why 5? How did you get the information from the expert? How do you transform that into that gamma distribution? So that's something we should be more careful. That is my message to the young people and the session, because I'm working with these engineers, and when I am lucky, I get opinions like the most likely value and upper lower bounds. And you will see here an example of how difficult it is to get information from the experts and transform it into a prior distribution. So we try to use as much as possible informative priors. Informative priors are the strength of the Bayesian approach. Regarding non-informative priors, you can use a lot of adjectives. I have some ones, if Jim Berger is not around, they are not Bayesian, I would say that. Let's say they are useful just to be nice to the people using non-informative priors. But now, yesterday, Andre made a citation by Bertolt Brecht, and I will start with the citation by Bertolt Brecht, the only one I know, from the same plot, which is it's Italian, Life of Galileo, but let's see what it is about. So, unhappy is the land and it's a hero. This is my favorite citation for Brecht. I like a lot of Brecht. In Milano we had a lot of Brecht plots at the Piccolo Teatro of Milano. But this is something which applies to the old days. In the land of statistics, in the old days, there were very few pioneers in Bayesian statistics. They were sort of heroes, like George Box, like Bruno De Finetti, Savage, and others. But then those days are over. Now there are a lot of Bayesians. Often I meet people who are very enthusiastic about the Bayesian approach. They think the Bayesian approach can solve all the problems. But that's the point that you have to be careful. We should be excited today, but tomorrow we will discover that there may be problems when we deal with the Bayesian approach, not only MCM, CIS, convergence, and what else. But what the basic, getting information from the expert and use it. So now I have a piece of poetry, which comes after this one, which is Italian, from Lorenzo de' Medici, Lorenzo il Magnifico, who was the Lord of Florence at the end of the 15th century, and he wrote many poetries. This is from Cantica Nascioleschi, and this is the start of the Canzone di Bacco, and it says: quante bella giovinezza che si fugge tuttavia, chi vuole essere lieto sia, di domani non c'è certezza. Maybe you understood. If you do not understand, here is the English translation I found on the web. How beautiful our youth is. There's always flying by us. Would be happy, let him be so. Nothing sure about tomorrow. So we are to be excited today, but tomorrow we might find problems with it. And just to finish, I have to cite another piece from one of the two books that we have to learn when we are in the Italian high schools. We have two books to learn. One is Divina Commedia by Dante Alighieri, and the other is Promessi Sposi by Alessandro Manzoni. And Promessi Sposi means promises spouses. And the citation is the following: Pedro, adelante con juicio. And that is something that the governor of the city of Milan, Spanish of course, was telling to his driver during the revolt for the bread in the city of Milan. So this is over avant-garde literature, Italian and German literature. Now, what I'm going to talk is essentially some methodological aspects and some case study. What the talk I'm giving is a little bit different from what you heard before, because as I said, I will look at the first stages of the Bayesian approach, and also I will try to look at some connections which are for me very important between Bayesian analysis and decision theory. This is really important because we always think in terms of beliefs, so assessing priors, using that, but also there is a terms of preferences, which means utility or loss function, decisions, actions. And it's important in cases like the one I'm going to talk to you about today, which is about an old work we did, but now we are doing something new about that. It's about some data we collected in the city of Milano about gas escapes in the city, and we have to decide about the policy of replacement of the pipes which are more keen to have gas escapes in the future. We did a lot of work, but today I'm just concentrating on one of them. So then here is, as I said, the idea is the replacement. And here is a sort of critical review of what we did in the past, in the sense that we did the following. We had some historical data, not many actually, luckily, because we are talking about gas escapes which could be deadly, and also we have some experts interviewed. So this is the big problem, how to get information, as I said, from the expert. And we asked them something about the propensity to gas escape in 8 classes of pipes. And then there is another issue. We have different opinions, how to merge them. So that's another important issue. And how to address that? Well, in the early 90s, we've been working a lot in what's called Bayesian robustness, and the idea in those days was to consider classes of priors and losses and their influence on what? In this case, we are ordering the different kind of pipes according to the different failure rates. The pipes with the largest failure rates is the one which has to be replaced the first. And if you want to know more about Bayesian robustness, there is a book I edited with Fabrizio a long time ago, 2000, and in which there is essentially the summary of what people have been doing about Bayesian robustness in the 90s. It's just called, I think, robust Bayesian analysis by EXCEEDANCE. But once you do this kind of analysis, you have a class of priors which are reflecting the opinions of the expert, then you have to make a decision and how to choose an action, how to find an optimal ordering. So there are some issues related to this one. And the one we are trying to work right now with these 3 Spanish persons as essentially in terms of decision analysis, so in considering non-dominated actions, and you will see here some properties of these non-dominated actions and some relation with Bayesian actions. And also we are proposing actions that we call least sensitive actions, which are compared with respect to other that I've been studying with other people a long time ago. One is the posterior regret I studied with Fabrizio and Brani Vidakovic, and conditional C-MINIMAX I studied with my colleague Bruno Beton. And also there is another important issue when you are dealing with people in the real world, engineers in this case. You need some graphical tools at different levels. There is an interesting paper by Deepak on Bayesian analysis in which he was presenting a way to elicit prior using graphical methods to help experts to elicit priors. Here you will see some graphical models which will help the expert to understand what happens a posteriori after he or she has made some decisions. So here we are interested in the replacement policy of these gas pipelines, and we did a lot of works. The one here is the simplest one because we are using homogeneous Poisson process. Homogeneous process because we are considering cast iron pipes which are not subject to corrosion. So the accidents, the gas escapes, of course, randomly, and they do not change over time because there is no corrosion. So the homogeneous Poisson process is the proper process to use. In the steel pipes, we consider a non-homogeneous Poisson process, and we went parametric or non-parametric by using gamma processes as well. But here the point is try to identify the most prone conditions under which the gas escape occurs. We did some study and we came out with 3 important features: diameter of pipes, laying location, and depth. You will see later what they are. And here we have decided all of these features as 2 levels, high and low, and putting all together we have 8 classes, and all of them are modeled by using independent homogeneous Poisson process. And each of them has its own parameter, lambda sub I, and the point is how to get the priors on this. And this is the difficult part. The difficult part is to get opinions from the expert on that, and what we used was a method I will introduce to you, which is called analytic hierarchy process. It's a controversial method, but in this case it was the only one we were able to use. You will see why. We did also Bayesian and MND estimation, hierarchical model, and we ran some networks, and we did also some sensitivity analysis. So this is very, very simple. The models, we are talking about 6,000 different pipe sections. It's a total of 312 kilometers in the city of Milano. So the likelihood is very simple. This is just the likelihood from a Poisson process, which depends on the time, which are 6 years, and the length of the network, which is 312 kilometers, and we have 150 failures. This is the maximum likelihood estimator. We were able to identify also the maximum likelihood estimates for each one of the possible classes, and here you can see the difference. So this is the laying location, which was sidewall rather than street, small diameter rather than large diameter, not very deep, not so deep. So these are the maximum likelihood estimates for all of them. So now we have to ask to do the proper Bayesian approach. Use data. We don't have many data coming from other companies for many reasons. First of all, the companies are not disclosing data about gas escapes. It's not in their interest. Sometimes also the conditions are different. In a city is different than in a city like Milan. There is the salt in a sea city, and Milan is quite far away from the sea. So there are different kinds of issues which are related and cannot allow us to use a lot of data. So we asked 26 experts about the propensity to have a gas escape in those subnetworks. The problem is the following. Can we ask the expert to give us a gamma distribution, as I said before, with parameter 3,5, or telling us something about the quantiles of the distribution of the lambda parameter? No way. Those experts are not able to do that. So what at least the one we dealt with, and many others we have been working with in other projects. So the idea has been to use qualitative judgments and transform them into quantitative judgments. So they work, these experts, in the world of qualitative judgments, and what we need, of course, quantitative one. How to transform that? Well, our students went to meet these 26 people, and they show them this kind of picture about all the possible configurations. These are the 8 classes. And the question they asked them was the following. For each one, comparing the classes pairwise. If a gas escape occurs, what do you think it will occur if you have to choose between subnetwork A and subnetwork B? So here, this is the answer they can give is, well, if gas escape in subnetwork B is equally likely as in subnetwork A, little more likely, much more likely, and so on. So there are possible, as I said, qualitative judgments about the propensity to gas escape. We transform them into a number. So you can say B, this one is corresponds to 1, 3, 5, 7, 9, and in between also this number. So for each one of the classes, they did a pair of classes, they did a comparison, and here we got a square matrix of size n, you can see here. So this is a typical square matrix, of course, comparing one class with itself, it's 1, comparing 1 with 2 gives 3 because it's a little bit more, and the opposite 2 with 1 is 1/3. So this is a typical matrix you get out of this method. And then what is the solution in this case? You look at the largest eigenvalue, and you look at the normalized eigenvector associated with it, and then what you get is this. So the probability of having a gas escape in class A1 is this one, class A2, class AN. In our case, n is equal to A. I will show you a little bit about the mathematics behind this. But you can see immediately what a problem with this approach. Because for me, much more likely than A, B much more likely than A, might be have a different meaning with respect to Andres or Rosangelo or Marcia opinion about that. For them, they might be definitely more likely than. So we may have different opinions about interpretation about this set. So this is problem number 1. Problem number 2 is about consistency. If 1 is compared to 2 gives a number 3, 2 compared with 3 gives a number 3, when you compare 1 with 3, you should expect the product of the two, 9. And often the person will give something which is not consistent. We know that people are not consistent. We have an example in my country. People kept voting for a guy who gave them nothing except bad reputation, bad economy, and so on, but they kept voting for that guy. Okay? So just to avoid me asking something about that guy, okay? I am against that guy. That is, I am consistent. Okay? Not my country. Okay? So strongly consistent if these judgments are such that there is the product. So the idea is to have this matrix written as W1, W divided by W1, W1 divided by W2. In this case, in this matrix, you can see that A sub ij is the ratio of these two. You can multiply divided by WK, and this is it. This is consistent. Unfortunately, sometimes people are not consistent, and you have to find a way to deal with that. If the matrix is consistent, this is just a matter of doing some computation, and you can write this as AW equal to NW, just a simple computation, and this is a system of homogeneous linear equation with non-trivial solution if and only if the determinant of this is 0. So there are, n is the eigenvalue of A, is the only value. So in this case, we have a matrix of rank 1, so that's why everything works, what I was telling you before, the eigenvector associated with the largest eigenvalue. That was the solution. Sometimes that's not possible, so there is some work by Sati, also some simulation. We did try to measure the sort of measure of inconsistency, but I will not go through that. So as you can see, this is a method which on one side allows us to get information from the expert, but it has a lot of flaws. And and once we are going to do a Bayesian analysis out of what we got from this approach, we have to take care of that. And these are the opinions by our 26 experts about the probability of having an event on one of these classes. And you can see a sort of consistency among them. The point is then how to put them together. So what we are doing is essentially the following. We are using the coloring theorem, which says the following. There is a Poisson process of arrivals, which are gas escapes, in the system, and then we are allocating to the different 8 classes by using a multinomial distribution. So we have, and what we get is essentially 8 different Poisson processes, independent one from the other, and the rate of them is equal to lambda times the probability of having one gas escape allocated to that class. This is the result. So we have the experts which are giving us the probability of gas escape in each one of these classes. The point here is how to choose this lambda. And here is what we should have done, and we did not do in those days because we wanted to do something easier. So we should have asked the expert something about also directly on this probability, and that we did, but then we should have also asked the expert about lambda, the rate, the gas escape rate in the whole system. In that case, we could have put then a gamma prior on it, but we didn't do that. we did something which was wrong, but I was young in those days, so please forgive me. So we estimated lambda by using maximal likelihood estimator, and then we did the following. So the expert's opinion became is a prior or lambda sub I, which was lambda hat, the MLE times the POI. Now I will not repeat this mistake. It's my sin, I understand that. And here there are some issues. This is a part of my talk to the young generation, is how to choose the prior. So gamma log normal. We had a long discussion with my colleague, the engineer from the Polytechnic of Milano, about the choice of the prior. He wanted to use log normal because engineers live in the Gaussian world. I live in the mathematical world and I like conjugate priors. At the end of the day, you will see the result. And also, so what we did was essentially the following: how to combine the opinions of the expert. We had 26 experts, which gave us some opinions on lambda sub I, and we used a sort of method of moments. We decided to get a gamma prior, and the mean and the variance of the gamma prior were equal to the sample mean and the sample variance of the 26 opinions by the expert. So we thought of the 26 opinion of the expert as a sort of sample from the prior distribution of lambda. And we did something like that. In a paper with Dipak and Elia Caglioni in the Chilean Journal of Statistics, we extended this method and also applied to the generalized mean value distribution. So we were able to compute the posterior mean of failure rate, and then we ranked the distribution according to the value of such posterior mean. The largest failure rate is corresponds to the class with most key to gas escape. And since we know that we were sinners, and because of the AHP, because of the lambda, and so on, we tried to recover for that, introducing classes of gamma priors with given mean and variance in some intervals, or with lambda in some interval. And we did some work on that. Also, we did some other work which is about empirical base. So we did the following. So the observation for each one of these 8 classes comes from a Poisson distribution, which with its own lambda and time. But then we try to introduce the covariates, which are the lane location, the diameter, and the depth, in the prior. So the prior we put on the lambda sub I is a gamma prior, in which the covariates appears here. So because with this choice of the prior, you know the expected prior mean is, the prior mean is this one, which depends on the covariance. We fixed alpha. In this case, we could do improper prior. What we did was empirical base. So if you do empirical base, how to choose this beta? So we have lambda, which is gamma, in this way, given the beta and given the data, and then how to choose the data? Well, just maximize the distribution of the data under beta, and then in that case, it's very simple to do it. But this is a double use of data, so that is practical. We do it sometimes, but again, this is not very, very Bayesian, if you want to be a very strict Bayesian. So this is actually the comparison we did at the end, and here you can see in the boldface the largest value in italics, the second to the fourth, by using normal, gamma, hierarchical, and MLE. And here you can see that these approaches, the worst class is the one which is anti-traffic with small diameter and not deep. Why that happened for the maximum likelihood estimator? Well, it's very simple. We're talking about a network of 300 and plus kilometers, and this class is only about 2.8 kilometers with 3 failures. If you had 2 failures, of course, we would be multiplied by 2/3, and it would be a very small number. So this is one of the things of the MLE approach. Here we used the expert's opinion, and we got these results. And you can see log normal and base similar result. After that work, my friend, the engineer, my friend, decided to stick to my decisions about the priors, so use the priors I wanted. Okay, so now there are some problems. As I said, I wanted to do some critical reviews of these past results, and we should have asked something different after some years of experience, something that probably the expert could have been able to answer. And they were more on the quantitative aspect. So, for example, we should have asked them, let's suppose we have a pipe which is 1 kilometer long. Let's consider 1 year. How many gas escape would you expect next year? I think an expert, one of those 26 experts, would have been able to tell us something about that. Also, it was impossible to say something about the median of distribution of the time of the first gas escape in 1 kilometer long pipe. So they can decide, let's say, the first time will be, let's say, 6 months. So having before 6 months or after 6 months will be more or less the same. So some statement like this one. So we should have done something like that, not what we did actually. And then out of that we could have considered this as a sample or lambda and or determining classical priors out of this. Also, we made a mistake of the mixed use of MLE and prior assessment. Also, the choice of the functional form. Who is the expert able to tell you about gamma? As I said, almost nobody. Here we tried to do something. Also, we decided to rank the classes based on posterior mean. And here is a relation with decision analysis. We know that posterior mean is the Bayesian optimal decision under square loss function. But is that the actual policy of the company? Does the square loss function reflecting the actual interest, utility of the company, the preferences of the company or not? So now we are going to use just actual, as much as possible, actual beliefs and preferences, and that means residual price and losses, and then ranking based on adequate actions. And here there is an important paper published by Heron and Rios, the father of my friend Javier Rios Ursua, in the first Valencia meeting book, 1980. They are addressing the issue of partial ignorance or partial uncertainty, which is compared with the notion of total ignorance, when we know nothing about the priors, and the perfect knowledge, which we know that there is a unique prior. Under this condition, they provide some axioms, some results, which are very important, very difficult to understand for me as well, and they provide a quantitative framework for sensitivity analysis in statistical decision theory. And they use non-dominated action. I will give you a definition of them a little bit later. And this is a basic computational objective in sensitivity analysis. Determining them is the important issue, and when we are interested in decision-corrected progress. They did the following. They associate to each action A a function L of theta A, and they consider the set of such function H such that there exists an action A belonging to the extra space capital A, such that H of theta is L of A theta for any theta, so this should be a large theta like this one. So here it is the problem. They're starting from actions, so we are in the decision world, and they have preferences. If we are able to state preferences among different possible action choices, what is the result? So here is all the condition and so on. So if all these conditions are satisfied, then there exists a class of priors such that it's possible to do the following. This is an ordering between actions. Here we say that B dominates A, is not dominated by A, it's a proper term, it's not dominated by A if and only if the expected loss of the choice of A is bigger or equal than the expected loss of B or any prior in the class. So this is the result which relates the having preferences on the set of the possible actions to a class of priors, and relates also to losses as well. So here let's give a definition of non-dominated actions. And let's suppose we have a class of loss function and a class of prior, and this is the posterior expected loss for a prior, an action, and the loss function belonging to this class. We say that an action A is a non-dominated if there is no other action B such that the expected loss of B is less than equal to the expected loss of A for any prior and any loss, and there is a pi naught belonging to gamma and the loss function belonging to L, such that the expected loss of B under them is strictly less than the expected loss under this one. So if this does not happen, then A is non-dominated. And should such B exist, then we use this notation. We will say that A is dominated by B. So why we look at non-dominated actions? Because when we have a class of loss function, well, considering only base actions may be somehow restricted, because as you can see, these are actions which have the nice property of not being worse than others. And what we are going to do is to discard dominated action and consider non-dominated set. And this may be, the non-dominated set may be possibly empty. This is a typical example. We wrote. Most of these are papers with Afinto Martin and David Rios. And actions A1, A2 in a space, which is this one. Look at this open space, open here and open here. These are the loss functions. The one L1 just loss function. This gives A1 for all values of theta. This gives A2 for all values of theta. And in this case, for any action A, there is another A prime which dominates A, because they go to 0. So in the limit, you can always find for each A one which is smaller, going to 0, which dominates this one. If you have a finite action space, then you get a non-empty, non-dominated set. And also, if you have a finite set, but non-empty, of base actions for one loss function, then there exists at least one non-dominated action. So also we proved another results about COMPUTATION space. So there are conditions under which it's possible to prove the non-dominated set is non-empty. Sometimes there is, so regarding the relation between the non-dominated actions and base action, well, I would say they coincide if there is a unique loss function in the class of curves. This is what actually we are doing. The reason which I changed a little bit the title is that currently in our work I'm doing with the other three Spanish person, we are considering only a unique loss function. So non-dominated action, base action, in that case, are the same. But there are examples like this one we prepare, and not entering in which there is a unique non-dominated actions, there are base actions, and there is no relation between non-dominated and base action. So they may be quite different one from the other. And if a unique base action exists for any loss function in L, so a set of base actions is contained in the set of non-dominated ones. And the conclusion could be proper. Here is an example we prepare about that. And there are other results like finite set of base action for a loss function, then one of them is non-dominated, and then if we have a unique base action for a loss function is non-dominated. So these are examples of other non-dominated action which might not be based. So there are a lot of properties. And an important issue is about computations of this non-dominated set. There are difficult aspects sometimes. There are some classes for which it's possible to do computations in quite easy way. For example, this one is one we proposed some years ago, is bands of convex loss function. Let's suppose lambda of t is a positive function, or negative null, if and only if t is bigger than 0, less than 0, equal to 0. Then it's possible to define a loss function lambda of a theta is the integral of this lambda of t between 0 and theta of a. So this is the loss function, which is written in this way, and this is the relation between capital lambda and lambda. There are many loss functions which are included in this class, like a square loss function, the absolute value, the Linux, and there are other possible classes you can write by using symmetrical loss functions to define convex loss function. Then the idea is to consider a class of loss functions such that the derivative of the loss is included between two functions b and ut. Under these conditions, it's possible to prove that the base actions for this loss function and the base action for this loss function are determining a set, and this interval is the set of both base and non-dominated actions. There are other results. One is due to Bielsa, David Rios, Peter Müller, which essentially they do the following, because these are difficult situations. So the idea is to sample a subset of actions and compute the set of non-dominated alternatives within AN, the subset. This is an approximation to the non-dominated set. Under some condition, this set of non-dominated alternatives converges to the true non-dominated set. So these are some results. And here, regarding what we are doing right now is the following. Now we're considering only 14 experts out of our 26, and we are considering empirical quantiles. So we have the expert who give us opinions on the lambda bias, and we are able to consider empirical quantiles, and out of that a class of priors with given quantiles. And we are considering a unique loss function, which is quadratic, so in this case a non-dominated set coincides with the set of base action. And here is the result, the graphical tool that I think is important for the expert. So these are the 8 classes, and here are the prior values of the lambdas given by the expert. So this is the range of the prior opinions by the expert. Here you can see the following. This class number 3 is probably the worst one. But we cannot be sure, because for this expert which gives this opinion, this is better than this other class. So this is reflecting the true opinion of the experts. We have nothing else added at this point. So how can we now go further? Well, as I said, these are the opinions by the expert, upper and lower bounds, and these are the empirical quantiles of the opinion. Out of this empirical quantiles, we are going to build a class of priors. So a class of priors, this was actually my first paper some years ago. I published it a long time ago, actually. This is the idea. Consider the class of all the priors such that they bear some quantiles, or if you prefer, the probability of some integral is given some value p sub I, and the interest is in the posterior mean, like in our case, and the result I proved a long time ago was the following. We are looking at the supremum or the infimum of such a posterior mean is that actually this one. So you have to find one point in the closure of each one of this each one of this interval, and you have just to solve this one. And we did now computed the ranges under the class of 3 and 7 quantiles. So we have here the 7 quantiles given by the experts, the empirical quantiles, and this is the results when we have 3 quantiles or 7 quantiles. So what we're doing now is the following. We are using the expert opinion, and we build a class over all the possible prior distribution, sharing the quantiles, the 3 or 7 quantiles. And then we compute the range of the posterior mean and in that class. So the range is the supremum and the infimum of the posterior mean. And here you can see with 3 quantiles, still there is some uncertainty. But when you go to a comparison from the gas company with this result, with 7 quantiles, so you are using data and the expert opinion, here is clear. For each expert you use, the result is very, very clear. So this is the worst class, which is actually the one I showed you before. So, but the point here is when we have a class of priors, and we are not certain about how to choose, it's not a clear situation, for example, like this one. Here is not clear because here there is some overlap between these two. How to choose one action. And here the idea is the following, is to introduce a notion of some optimality criterion which will lead us to choose one action which is optimal according to some criterion. And here is a paper I wrote with Silas Baganese some year ago. We introduced this notion of relative sensitivity. So we are interested in the following. Yes, class of priors. We are considering the expected value of the quantity of interest. Here is h of theta, the posterior mean of that quantity, under a prior pi naught, and then we consider, so this should be small pi naught, and then we consider the expected value under another prior, and we compare the two of them, square them, and divide it by the variance of such h of t with respect to the posterior mean corresponding to this pi. So here I make to this pi. And this has some property which is scaling variant, calibration, but also the important aspect is the following. It is a decision corrected interpretation. What does it mean? If the relative posterior expected loss increased by considering pi naught instead of the 2 pi, it is something of is equal to this one. Let's see the following. So we have a square loss function, so we are interested in posterior mean as base action. Pi naught is the chosen prior, and rho naught is the base action. Let's consider pi different from pi naught, and let's suppose this is the true prior, and rho pi is the true base action. So instead of using rho naught, we use rho naught instead of rho pi, and the expected loss in choosing this prior, using this one instead of this one, is this one. We know that the posterior expected loss by using the base action is actually equal to variance, but in this case, this is the error. And if you divide everything by this quantity, you will see that this quantity of our interest is the relative increase in expected loss. And the supremum is the maximum expected loss over all possible 2 priors in gamma. There are other aspects of asymptosis. And here is what a few years ago we proposed with the 3 Spanish people I'm working right now, is an extension. Instead of consider, so here we have a posterior expected loss, So a general loss function, and here we are considering the difference between the expected loss under a prior pi and the expected loss under the same prior pi and in this case there is also a loss function L, and this is the base action divided by this one. It's just an extension of the previous one. And what we are doing here is the following. We are introducing the notion of least sensitive action, which is the one which minimizes over all possible action the maximum of this quantity. These are non-dominated but necessarily based. In the last two, I still have 5 slides, but in 5 minutes I can do that. There are 2 other concepts which have been considered by myself some years ago, as I said before, posterior regret. So the posterior regret is the expected loss by using an action A when you have a prior pi and the loss function L, with respect to the one you should have by considering the base action. And the posterior regret, L gamma minimax, there is just gamma, G, this, is the following. Let's find the action such that it minimizes the supremum of this posterior regret. This is the PRG action. We proved with David Riosa and Brani Vidakovic that for square loss function, this action is actually the middle point between upper and lower bounds defined on the posterior mean. And under such conditions, we proved also that they are base actions. In another work with Bruno Betro, we were interested in the conditional gamma minimax, essentially finding the action which minimizes the sup of the expected loss under the prior L and pi in this kind of classes. And here, in general, our new proposal is that these sensitive actions is in general better than these two. Because our original idea was the following. We have a class of priors, we have a range of posterior means, for example, of estimator, and if this range is small, that was the interest of Bayesian robustness, if the range is small, then we can choose each prior we want in the class, and the result more or less is the same. But if the range is large, the difference between supremo and primo is large, how to proceed? The idea is the following: to report the range, but make a decision about one action to take. How to choose this action? Some optimality criteria. We proposed PRGM, we proposed CGM, but now with this new idea, we are getting something which is, in our opinion, better because we are minimizing the relative error with respect to base action. We always have to try to look for base actions, but in this case, we are trying to find something which is as close as, which is probably a base action, and it is often, but is as close as possible to the best to this base action. And here we did the following for different kind of actions. This is the ordering. So here you can see another issue, which is the ordering of the classes is essentially robust with respect to the choice of different criteria, optimality criteria. And just to conclude, another work we are doing right now, which is, I think is important for, this is new, with respect also to the previous work, if you have to decide to replace or not, we have to decide if there is a threshold. If we exceed some threshold, so we're interested in the probability for each one of these pipes network of lambda exceeding some threshold given the data. And when we have a class of priors, the decision is the following. If the sup of this probability is below some acceptable risk alpha, then do not replace, because for any prior you choose, the posterior probability will be below the acceptable risk. Replace is the infimum, is less than alpha. That means all possible probability you choose, you will get a value of probability which is above the acceptable risk. Otherwise, further investigation. And the tool we are proposing is something like this. Here is for the class with 3 quantiles. Here you can see alpha, this is the acceptable risk, and here you can see upper and lower bounds on the probability. When you go up to here 0.21, but if this is the threshold that you are setting, if it's less than 0.21, then replace the pipes. For any prior, you will get a value such that the probability, the posterior probability will be above 0.2. If you are here, which is 0.32, then all the probabilities with all the priors we can choose will lead to a posterior probability which is below the threshold. And just to conclude, these are other quantities that are interested, threshold, the number of filtered class escapes, other classes I considered with Bruno Betro and Mara Pecharski a long time ago, and then move to classes of loss. And that's all. Thank you.